Hi everyone, my name is Eric, and in the following period of time, I will be learning number theory with you guys, whoever is in front of the screen. Now, in order to learn number theory, you have to know what is number theory, and in fact, it is much simpler than you might imagine, and it's basically the study of the set of positive whole numbers. Now, you guys probably know what positive whole numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, mind you, there's no 0 because it's positive whole numbers and 0 is neither positive nor negative, so we cannot include 0. And in this set of positive whole numbers, there are unlimited other little sets, not unlimited, but I believe we'll find more and more unique sets later. So there are even and odd numbers, obviously. 2, 4, 6 are even numbers. 1, 5, and there's another 3 that I missed. 1, 3, 5, 7. There are odd numbers. And also, there are Fibonacci numbers, as you guys probably know. 1, 1, and then 1 plus 1 equals 2, 2 plus 1 equals 3, and so on. As I've said, there are a lot of unique lists that we will be discovering while learning number theory. Now, these are typical questions of number theory, just to warm you guys up, to let you know what number theory questions actually are, and they're not very complicated. It's basically, I'm just gonna list some questions and you'll see what I mean when I say it's not complicated at all. So, first, there is the sum of squares. Possibly you guys know what square is. So basically, squares is a number, for example, 3 with a little 2 on the upper right side. And that little 2 means times the number itself by 2 times. So it's basically 3 to the second power, we can call it 3 squared, equals 3 times 3, which is, of course you guys know, it's 9. Now, the sum of squares, probably you guys also know the Pythagorean theory. 3, 4, 5, 3 squared plus 4 squared equals 5 squared. Now, the typical question of number theory, even if it's not listed in this place, in the PPT, it is basically, are there infinitely many numbers are there infinitely numbers that fit a squared plus b squared equals c squared? And also there's the second sum of squares question, x equals a squared plus b squared. For example, 5 squared equals 1 squared plus 2 squared. Also you can say 5. No, it's not 5 squared, it's 5. So are there infinitely many x's that fulfill the equation x equals a squared plus b squared? And also there's the sum of higher powers. A to the nth power plus b to the bth power, nth power as well. Sorry, not bth power, nth power. Equals c to the nth power. Now, the nth power, you guys also probably know since I just said the second power. A to the nth power, it's basically a times a for n times. So to the second power times itself by 2 times, to the fifth power 5 times. Now, we know that for the second power, we had already proven it to be fulfillable. Can we do it with cubes, which is third powers, or fourth powers, or even fifth powers? We do not know. Or actually, we do, but it would be very complicated to prove it. Now, are there an infinite number of primes? Of course, primes are just numbers without any other factors other than 1 and itself. So for example, 2, it's only got factors 1 and 2, and 2 is the only even prime. Now, infinitude of primes, you guys probably say that there are infinitely many, but what if there aren't? We do not know. And there are also number shapes. Now, you guys might be wondering, what are number shapes? Or is it like 6 and 7, how you write them? No, it is not. And if you think so, you're wrong. Number shapes are not how numbers are shaped, but how numbers can be shaped. This might be a bit complicated when I say it, but look at these triangles. So it's 3 dots, as you can probably see already. It's 3 dots. 3 dots make a triangle, and you call it triangular numbers. 3 is a triangular number, and that is number shapes, like how you can arrange a number of dots to be a shape. That is the easiest way I can think that I can explain it. And also there are 6 dots in this triangle, and of course 6 is another triangular number. Now it also goes for squares. 2 squared is 4, and look at this, 4 dots forms a square. 9 is also a square number. Now this is a very famous equation, and it is probably the most beloved of your teachers. It's just this thing. And now you guys might be wondering, what the hell is this? Well, it's nothing but it's like when you go ahead calculate 1 plus 2 plus 2 100. What you do is you add 100 to 1, and you multiply it by 100 over 2, and that is basically what this equation is about. So now, how we think of this equation? Well, look at this. 1 plus n, 2 plus n minus 1. It's basically 1 plus n. They're both 1 plus n. So there are n over 2 groups of 1 plus n. And that is how we get the equation, right? Wrong. This is how Gauss got the equation. Just look at this. It's not what we think how he got the equation. So he basically gave an example in his mind. So he's like, okay, let's say we want to get 1 plus 2 all the way to 6. Then he figured out, look at this. Look at this triangle. It's got 6 dots on the side. 1, 2, 3, 4, 5, 6. And the squares, the triangle's area, well, 1 plus 2 plus 3 to 6. Now, if there are 2 triangles and we connect it together with a line with n plus 1 units, which is 7 in this case, then we can form a square, which is n plus 1 squared in area. So in this case, it's 2 of these 1 plus 2 triangles all the way to 6, and we add it by 7. This is the line that connects them together, and we get 7 squared. Yeah, we do. So I'm gonna rewrite this equation since I did accidentally click the wrong button. I'm very sorry, guys. So why is this? Why am my brain doing this to me? Well, in order to get one triangle, we do not want a square, we want a triangle. We want the 1 plus 2 plus 6. We do not want 7 squared. We want 1 plus 2 all the way to 6. Now, how do we do that? We move 7 to the other side of the equation. That gives us, I'm not gonna move this side except for that 7. We're gonna erase it. It's not there anymore. It's gone. It's already here. So basically how we move this is we subtracted both sides of the equation by 7, and how I like to speak of it is we move the 7 to the other side of the equation, like crossing the road. Now, we do not want 2 times 1 plus 2 plus all the way to 6. We just want one of them. We do not want 2 triangles. We want one. So now what we do is we divide both sides by 2, and we get 1 plus 2 all the way to 6 on the left hand side of the equation, and on the right hand it's 7 squared, which is, we're not going to write it as 7 squared, we're going to write it as 6 plus 1 squared, in order for you guys to understand how the equation come naturally. So it's basically this thing, and if we get the numbers out of the parenthesis, we get 6 squared plus 2 times 6 plus 1 minus 6 minus 1. Now the plus 2 times 6 and the minus 6 gives us 1 times 6. We're just gonna write it as 6, and plus 1 minus 1, goodbye. So it's basically 2 over 6 squared plus 2. And just in case, if you guys don't know, a plus b squared equals a squared plus 2ab plus b squared. And I am running out of place, so let me erase this real quick. Oh, sorry, 6. Well, we see that there's a common factor of 6 in 6 squared and 6. So we get it out. Goodbye. And we have 6 plus 1 on the inside. Now, if we will look at that, 6 times 6 plus 1 over 2. Let's say n equals 6, then this equation is equal to this, and that is how Gauss got it, by using this shape. It's kind of unnecessary, Gauss. Now there are also the twin primes. Like twins are usually very close, right? So are the factors primes. Now twin primes are basically if n is a prime and n plus 2 is also a prime, then n plus 2 is a twin prime. For example, 3 and 5. Now you might say that there is a big O 4 over here. Well, we're not gonna write that since 2 is the only even prime. There are also the question of, I believe you guys already know what we're gonna ask about twin primes. Are there definitely many twin primes? No, we do not know. And also, primes of the form n squared plus 1, for example, 5 equals, I already spilled the beans, didn't I? 2 squared plus 1. Are there definitely primes like that? We do not know. Now, in order to answer these questions, we cannot just get infinitely many questions and no answers. That is bad. We do not want that. We want answers. So how do we get answers? Well, we accumulate data, and then after accumulating data, we examine the data and try to find patterns and relationships. So for example, 1, 1, 2, 3, 5, 8, we find that the 1, 1 is the starting point. We're gonna write it as STA. I do not know where that inspiration came from. And 2 equals 1 plus 1, 3 equals 1 plus 2, and so on. And you need quite some mathematical logic to actually find the relationship. And after you found a relationship, as a tongue twister for me, test your conjectures by collecting additional data and see if your pattern is correct. For example, in the Fibonacci, I can't really get an example where it is wrong, but you guys know if you get a pattern that you think is correct and then you write the next term and you find it wrong, it is frustrating, right? Then devise an argument after making sure it's correct, of course, or else you'll never be able to prove it, ever. So you devise an argument and check how you can prove your pattern in the list of data. Now that is it for today. Next time we will look closer at Pythagorean numbers and how to find them and what are PPTs, not PowerPoints, primitive Pythagorean terms, not PowerPoint. Okay, so this is it for the introduction of number theory, and it's just the tip of the iceberg, not even the part where it's visible. It's basically the, wait, let me go ahead into edit mode. So if an iceberg is like this, we basically only touch the tip of it right here. Now we want to see the whole iceberg, so we'll have it will get more and more complicated later on. And for Pythagorean numbers, even though it's just the second chapter, we already have to use squares in order to prove it. So prepare, you guys, and that is the end for today.